Physics, Electricity, Lecture 3. Okay, so we're continuing our talk about resistance, which we started yesterday, actually. So if you can write this down, we're looking now at something called resistivity. Alright, have you got that? Right. So, let's have a look now. So not too much to do in this first lesson. Right. All electrical devices, light bulb, TV, PC, mobile phone, iPad, tablets, every electrical device has a resistance. Everything. So, if this TV, a current passes through the TV and the charge loses its potential energy because this energy gets turned into light. So we say that there's a voltage, there's a potential difference. So this TV may be, whatever, 200 volts. It means for every coulomb of charge that goes in, the coulomb of charge comes out, losing the ability to do 200 joules of work. And so because it loses this ability to do work, because the work was converted into light, we say it has a resistance. So every electrical device has a resistance. Every electrical device. A resistor, though, is a particular electrical device that has a fixed amount of resistance. This is what a resistor is. And it's used in experiments and circuits, and normally the work done is heat. Now I do have one actually, wonderful, because I was doing the experiments. with the September students. Here we go. Here's an example. So this is a little resistor here. So if a current passes through this, there will be a resistance. So then if there's a resistance, it means some of the potential energy was converted. So what do you think? What energy comes out of this? What form of energy? Yeah, it's heat. So these little resistors, really they're just like little heaters. The heat is so small you can't even feel it. It's like it almost feels like there is no heat. So that's a resistor. I think I have another picture of one as well. But you can buy these online. Whatever. Okay. Small resistors are really just small heaters. Here's an example. Here's a picture of one. This is, for example, maybe a 1 ohm resistor. So that means every time a coulomb goes in, the coulomb will come out, losing the ability to do 1 joule of work because 1 joule of work was done as it travelled through, and the form of the work done was to produce heat from the resistor. So what I'd like you to do is just to draw this picture as an example of what a resistor might look like. And you should write something down as well. You should say something like a resistor has a fixed resistance, or something to go with this picture. Don't just draw this picture. What the heck is that?
Yeah.
That's that?
Okay.
Alright. Yeah, okay. Yeah. Roughly the same.
Why do we need this resistor on the circuit?
In fact, it seems like it's a waste. Like, why would you use something like this? Because it's just wasting energy. But we'll see later in the chapter that we can use these we can use them in special ways that let us do useful things. Like, for example, maybe we want to change the voltage and we have too much voltage or something. We could use one of these to reduce the voltage, Like, for example, this provides 220 volts, whereas maybe the TV needs only like 20 volts, you know. Anyways, we will see it later, okay, don't worry. Continue? Yep. Okay, let me just turn my tablet on. Okay. So what affects the level of resistance in a resistor? So we have this resistor here, here's a picture of it, and I want to know what might change how much resistance there is. So, what are the factors that change how big the R is? So, first question, do you think the length affects the value of R?
Yeah.
Yeah, it does. To increase or decrease it, what do we think?
More length, more
resistance. Yeah, okay, so the answer is yes. What about the diameter, the radius? Will that affect the resistance?
Yeah.
Yeah, it does, of course. The type of material?
Yeah.
Well, yeah, of course, because if it's a conductor, that's less resistance, and if it's an insulator, that's more resistance. So, putting these all together, you can actually arrive at this formula. Now, before you write it down, let me just explain each part. This is the total resistance, and it depends on the length. So you can see that if the L is bigger, the R is bigger. It depends on the cross-section area. Now this is interesting. The bigger the area, the smaller the resistance. And this constant here is a constant for the material called the resistivity constant. L is the length, A is the area, and rho is a constant which is different for each material. And it's called the resistivity, which we'll get to in a moment. So, can you write this definition down? This is the formula for the resistance in a resistor. Got that?
And the R is the resistivity.
The R is the resistance, the total resistance, and this rho is a constant called resistivity.
So R is the same as the R we used yesterday?
Oh, it is. It's the R from yesterday as well, yeah. Okay. No, not just yet.
The unit is ohm, then.
Oh yeah, because it's just the same as yesterday. Yeah. Continue? Yeah. Okay. So, what exactly is this constant? So this resistivity, it measures how much electrical conductor stops the flow of electricity through it. Most metals have a low value, and the units used are, so you could actually work out the units here if you rearrange this, but we'll just go straight to the answer. The units are the ohm meter, and it's for measuring how much electrical resistivity there is here. Now, you don't need to write all of this down, and in fact in the exam, the definition they want is a little bit different. There's this kind of trick here for getting the definition in the exam. You can do this, let me show you. You know R equals rho L over A. So sometimes in the exam they ask you for definitions of constants, like here. Or remember we have Young's modulus, which is stress over strain. So in the exam, if they asked you what is the definition of Young's modulus, well, that's easy. You can just say Young's modulus is the stress divided by the strain, or the ratio of stress to strain. And you can do the same trick here for resistivity, but first you have to rearrange it. So you can say this. So in the exam you would say the resistivity constant is the product, and product means multiply, of what? Resistance and cross-sectional area, but then we have to divide. Yeah, so what's the word when we divide in a definition? Huh? Per, yeah. The product of R and A per length. Yeah, per unit length. So it's kind of like a simple trick for definitions of constants in the exam. It's not really wonderful, but it's what they want in the exam, so it does just fine. It's not even asking the student to memorize anything, because, you know, this formula is in the formula book, so it's not even asking the student to memorize anything. It's just asking them to rewrite it and then put it into words. So it's the reason I don't have that definition is because that definition doesn't tell you anything, whereas at least this definition tells you some meaning. So the meaning is, it's big, it means it's an insulator, and if it's small it means it's a conductor probably. Continue? Yeah? Okay, so we'll continue now. So we kind of understand what an insulator is. An insulator is like a plastic, something like this. But if I try to be a little bit more formal, or if we try to be a bit more formal with the definition, we could say an insulator will offer an appreciable level of resistance. So what I mean is an insulator has some high level of resistance that we can notice. And this usually means it has a high level of resistivity. Now this isn't always true, it's usually true. So an insulator will have a noticeable, an appreciable level of resistance, and also, not always, but also usually a high level of resistivity. So we call this material an insulator, like a plastic. Plastic would have a high resistance, and plastic materials have high resistivity constants. Okay, so if you can write this down, that would be great. Now this isn't necessarily an exam definition, it's just for your notes. Whose book is this? Interesting. Okay, next one, you can probably guess what the next one's going to be. Conductor. So, what's the difference? Well, you can probably guess a conductor will not offer a noticeable resistance and will often have a low resistivity constant. No big surprises. What you expected. Now, the reason I say not always is because, you know, you could make a resistor out of a metal, you could make a conductor out of an insulator. It's all just a matter of scale. So for example, you can make your metal so that it actually is a resistor rather than a conductor. So, yeah. Continue. So, I think I should give you some values now. So we'll have the material, we'll have the resistivity, and if we consider it an insulator or a conductor. The first material is carbon, graphite to be precise, like in your pencil. And believe it or not, this is actually considered a conductor. And it's a good conductor because this constant is so small. Ah yes, I will demonstrate this. Who has a pencil? You've got a pencil and a piece of paper. Oh, my students are so good. They put everything back so neatly in the box. Great! Wonderful. Wonderful, wonderful, wonderful. Okay. Okay, let's see now. I'm not doing anything exciting, I'm just making a pencil mark on the paper. I think that should be enough. Right, so this here is what's called a multimeter. Multi meaning many, because you can actually change it into a voltmeter, an ammeter, or a ohm meter. So right now I would like to make it a voltmeter, so I'll set it to millivolts. Millivolts. There we go. Right. Now let's see. That's there. That's there. Okay. Hope this works. And you can have a look in a moment. So it's jumping around, I guess, because millivolts is volts, which is just a moment. Okay. So it's nearly jumping a little bit. It should be 0. Okay, and it's still 0 here. Actually, do you know what? I don't. No, I need to have a battery, of course. Yeah. All right. Let's try this again. Right. So let me see. Battery. So what I'm doing is I'm going to show you that I can actually use the pencil as a conductor to have the current travel through the pencil. So I need a battery, so let me put that there. Can you hold these together? Now it won't hurt much. Yeah, no, I'm just joking. Don't, it's okay. Need to get some crocodile clips. And that in there. Okay. Right. Don't worry, I'll show everybody now in a second once I get it connected. Okay, and this one here, and I'll clip this here, right, and I'll just hold this here, and we'll put it to min amps. Oh, you're embarrassing me. This is supposed to work. Now hold on, don't give up so easily. It's not pushed in all the way, maybe. Yeah, no, this is embarrassing. Maybe something's broken. Maybe it's the pencil. Maybe I don't have enough mark on it.
You don't have a piece of lead.
You have a piece of lead? Yes. Thank you. This is not making enough pencil for me. All right. If you can give me one to borrow. How do I open this?
Just do.
Just shake it out. Yeah. Whoa, don't break it. Right, hold on. Right, let's see now. So this is the pencil carbon. Steady. There we go. So, yeah, the battery just backwards. There we go. So right now, there is 146 milliamps that can pass through this carbon. So this carbon, can you see here? I can use this as a conductor to complete the circuit. It actually works. So yeah, that might be surprising. Maybe some of you didn't know that actually carbon in your pencil is actually a very good conductor. It's like as good as a metal. But I think it's maybe, it has disadvantages, like why would we not use carbon? Why do we use metal? Why would we not use this in a circuit? Yeah. With the metal you can change the shape quite easily. It's plastic, whereas the carbon is brittle. You can snap it, so it wouldn't be used in a circuit. But I do promise you, if I keep drawing this pencil on the paper, I have done this before, you can trust me, I didn't imagine it. On both sides? Yeah, probably. I don't think I have it thick enough. Oh well, I've shown you with the carbon anyways. Alright. By the way, I think every good engineering student should have one of these at home, because I find them so useful. For example, when Dennis's laptop broke, wasn't getting any power, I was able to check using this if there was a current here, because it's good to know, is this broken or is that broken? Because if you can see that this has no current, then it means you only have to buy a new one of these. Yeah. But if you can see that this has a current and your laptop still has no power, then it means something with the laptop. And then you can take the battery out, and this has a battery setting as well, so you can actually check your voltage of your battery. Actually, let's do that since I have this in my hand. Would anybody like to give me their phone battery? Trust me, I won't break it. Fine, I will. Oh, lame. Right, I'll use my phone then. Right, so let me set it to the battery setting. So, if I take the battery out, can you see on this? It says it's a 3.7 volt battery. So let's test that. Okay, hold on now. I'm sure I know what I'm doing. Come on. I can't quite get it. It's too small. Come on. No, can't get it. Anyway, this one's a little bit too hard because it's too small, the little holes. But you can do this to test your battery. So what will happen is when your battery's getting old, the voltage will be less than what it says on the package. So this is 3.7. I expect to see 3.6 or 3.7. When the battery's getting old, it might only say 3.4 or 3.5. So it's a way you can check the health of your batteries to see if it needs replacing. Anyways, like I said, every good engineering student should have one of these at home. They're only about $20. They're very useful.
Are you going to sponsor?
Actually, maybe I should get sponsorship for X-Tech Instruments. MN35 multimeter. I'll make sure I didn't break my phone.
Great.
No, that's fine. Alright. There's an option on the multimeter to check the current in this as well. I'm not brave enough to do that. It's a bit too risky. Okay, so first material is graphite. Did you write this down? Next one is copper. Copper is also a good conductor. Actually, you should have a multimeter if you want to do any more pi projects with the pins. You remember you showing me the video of your project you did in school?
Oh yeah,
Yeah, so you can use the multimeter to make sure the pins are working.
we have one at school.
You have one at school? But what about your own personal one, just for you? No?
We might have one at school.
You might even have one, okay. Right, next material is nickel. Nickel is what they used to make the coins out of, but not nowadays. But the coins, the money used to be made of nickel. But actually now nickel is too expensive. Next, got that? Nichrome. This material is also a metal alloy, and it's good. It's a good material for, I think, making electric heaters. If you want to make an electric heater, I think they use this material. Okay, next now onto some insulators. Now, can you see the big difference between this and this? So it's a huge difference between a conductor and an insulator, like 10 to the 20. It's a huge value change. Okay, next material after wood is rubber, also an insulator. Not quite as much as wood. Okay, you got that? Yeah. Right, so you could make a resistor actually out of a conductor, but it's not the resistivity that you care about, but the total resistance. So this is just part of the formula. Let's have a look at our first example. I think I only need to do one example because there's only one formula. An electric heater. Does anybody have an electric heater at home? You know, like the ones in the cab room. They're electric heaters. They're very, very, very simple. All they are is just a piece of nichrome, and the current passes through the nichrome, and that heats up, and the heat leaves the heater. So they're very, very simple. Very, very simple. You could make one. You could make one at home, but not amazing. So if you have some nichrome, and we'll say it's 20 centimeters long and 5 millimeters in diameter, then what is the resistance? Okay, so if we can take out our calculators and use the formula. So if you look at your table, we'll need the resistivity of nichrome. If I got my calculator open. Come on, let's open this piece of junk. I'm waiting for my calculator. There we go. Alright, so first we need the constant. What's the constant for nichrome?
1.1 by 10 to the power of -6.
And then we have it times the fraction. So on the top is the length. What's the length?
20 by 10 to the power of -6.
Good. And then on the bottom we have the area, which is pi r squared. Now what's the r here? Be careful. 2.5 millimeters. So we'll do 2.5 times 10 power minus 3 because it's millimeters. And like you said, actually, maybe I'll write it the way you said it. 20 centimeters. So it's 20 10 to the minus 2. Yeah. Okay, so let's see if you got the same answer. So 0.011. Now that's not really a real answer because for a real electric heater it's more than 20 centimeters. The wire inside it goes like this. So maybe if you were to pull it out it could be like, I don't know, 3 meters or something. So if I just change this to 3 meters, let me just see what I would get. Yeah, still small. Okay, we got this one? Yeah, so not too difficult, not too difficult. How many questions did I give you for this? Oh yeah, easy peasy. You should get these done in a few minutes and then we'll start the next lesson. So it'll only take you 5 minutes, they're very short.